You're sitting in an airplane somewhere above the clouds, cruising at 35,000 feet. Outside, the temperature is around minus 60 degrees Celsius. The air is so thin up there that if you opened a door right now, you'd lose consciousness in seconds. The pressure difference between inside the cabin and outside is so extreme, it's essentially the difference between life and death. And in the middle of all that, there's a tiny hole in your window. Not a crack, not damage, a deliberate, perfectly placed, engineered hole, sitting right there, in the one barrier between you and that deadly outside environment. Now your brain is probably doing one of two things right now. Either it's saying, wait, what? Or it's saying, I've seen that hole 100 times and never thought about it. Either way, the answer to why that hole exists is one of the most quietly brilliant pieces of engineering in the history of aviation. And once you understand it, you will never look at an airplane window the same way again. Let's start from the beginning. When an airplane takes off and climbs to cruising altitude, the world outside becomes genuinely hostile to human life. At 35,000 feet, atmospheric pressure drops to roughly a quarter of what it is at sea level. Your blood would literally start to bubble. Your lungs would collapse. The air is too thin to breathe. It's essentially the edge of survivable atmosphere. So the aircraft has to create its own environment inside. The cabin is pressurized, meaning the air inside is kept at a comfortable pressure, roughly equivalent to being at 6,000 to 8,000 feet altitude. That's why your ears pop when you take off and land. The pressure is being adjusted. But here's where the physics gets interesting. When you have high pressure on the inside of a sealed tube, which is basically what a fuselage is, and extremely low pressure on the outside, that pressure difference creates an enormous outward force on every single surface of the aircraft. The walls, the floor, the ceiling, and yes, the windows. Every square inch of that aircraft's skin is constantly being pushed outward by the pressurized cabin air trying to escape. This is called the pressure differential, and it is relentless, every single flight. For hours, for thousands of cycles over the lifetime of an aircraft. Now think about what that means for the windows. Airplane windows aren't like car windows or house windows. They're not a single pane of glass. They're actually a system, a carefully engineered, multi-layered system. And this is where most people's mental model completely breaks down because most of us assume it's just one piece of clear material keeping us safe. It's not. A typical commercial aircraft window has 3 separate panes, 3 layers, each one doing a specific job. The outermost pane is part of the aircraft's actual structure. It's embedded into the fuselage, and it's built to handle the full pressure differential between the pressurized cabin and the outside atmosphere. This is the load-bearing layer, the one doing the heavy lifting, flight after flight. It's made from stretched acrylic, a material chosen because it's lightweight, optically clear, and incredibly strong under stress. The innermost pane is the one you can actually touch. It's the scratched-up layer your elbow rests against, the one you press your face to when you're trying to see the city lights below. This pane is essentially a protective barrier. It keeps passengers from touching or damaging the structural layers, and it provides a bit of thermal insulation from the freezing cold outside. And then there's the middle pane, the one in the middle, the forgotten pane. The one that almost nobody talks about, but this is the one that matters most for our story. Because that tiny hole, it's in the middle pane. It's called a bleed hole. Sometimes engineers refer to it as a breather hole. It's typically just 1 to 2 millimeters in diameter, barely noticeable. But it does 2 critical jobs simultaneously, and if you removed it, things would go very wrong, very fast. Here's the first job. Remember that pressure differential, that constant outward push from the pressurized cabin? Well, that force doesn't just act on the outer surface of the window, it acts on every layer. If all 3 panes were sealed completely with no way for air to move between them, the pressure would build up in the tiny gap between the middle and the outer pane. That trapped air would be at full cabin pressure, pushing outward against the outer pane, and pushing inward against the middle pane, both panes under full load simultaneously. That's not ideal. The bleed hole changes this completely. Because the hole is in the middle pane, the small air gap between the middle pane and the outer pane stays at cabin pressure at all times. The air just bleeds through that tiny hole, slowly, constantly, equalizing, which means the middle pane essentially has the same pressure on both sides of it. No pressure differential across it whatsoever. It's carrying 0 load. The outer pane, meanwhile, has full cabin pressure pushing out on one side and the thin, freezing outside atmosphere on the other. It carries the entire structural load. It's designed specifically for this. And here's the genius part, the part that engineers thought of decades ago that most passengers never realize. By relieving the middle pane of any pressure load, the engineers created a backup system. If the outer pane ever fails, if it cracks, if it develops a fracture, if something goes wrong, that middle pane, which has never been under pressure load, never been fatigued by the pressure cycles, is now the last line of defense. It's fresh. It's at full strength. It's been resting its entire life, waiting for this moment, and it can handle the pressure. Think of it like a spare tire that never gets used until you need it. Except the spare tire is keeping you alive at 35,000 feet. The engineering logic here is almost beautiful. You're looking at a system designed around the idea that the thing you see every day is already planning for the day it breaks. Every single flight, the outer pane is working hard, taking the load, enduring the stress, and right behind it, separated by a few millimeters of air and one tiny hole, is a perfect, pristine backup just waiting. That's not accidental. That's the result of aviation engineers thinking through every possible failure mode and building in layers of redundancy. Aviation doesn't just build things to work. It builds things to still work after part of them has stopped working. But the bleed hole has a second job. And this one is something you've actually seen with your own eyes, even if you didn't realize it. Have you ever noticed that the innermost pane, the one you can touch, sometimes has a faint fog or condensation on it, especially on cold days or long flights? That's because the temperature difference between the warm cabin air and the freezing cold outside creates conditions where moisture in the air wants to condense on cold surfaces. Now, without the bleed hole, that moisture would get trapped in the air gap between the middle pane and the inner pane. It would condense on those surfaces. It would fog up. It would obscure your view. But more importantly, over time, trapped moisture causes problems. It degrades seals, it potentially leads to ice formation, and it reduces the integrity of the window system over time. The bleed hole prevents this. Because air is constantly and slowly circulating through that tiny hole, the humidity inside the gap between the middle and outer panes is constantly being refreshed with cabin air, which in long-haul flights gets progressively drier as the flight continues. The moisture never gets a chance to build up. The gap stays clear. The panes stay dry where it matters. So that one tiny hole, smaller than a drinking straw, is simultaneously managing structural load distribution, maintaining a backup safety system, and controlling moisture and humidity. 3 engineering problems, 1 2-millimeter hole. This is why aviation engineers genuinely love this solution. It's what they call elegant. In engineering, elegant doesn't mean pretty. It means solving the maximum number of problems with the minimum possible complexity. No moving parts, no electronics, no sensors, no maintenance required. Just a hole, doing its quiet, invisible job every single flight. Now, here's something that makes this even more remarkable when you think about the scale of it. A commercial aircraft like a Boeing 737 or Airbus A320 might fly 5, 6, sometimes 8 flight cycles in a single day. Every time it climbs to altitude, the pressure differential builds. Every time it descends and lands, it releases. The fuselage and windows go through what engineers call a pressurization cycle with every single flight. And over the lifetime of a commercial aircraft, which can be 20, 25 years, those cycles add up to the tens of thousands. Each cycle is a pulse of stress on the structure. Expand, contract, expand, contract. This is why metal fatigue is something aviation engineers think about constantly. Materials under cyclic stress eventually develop microscopic cracks. It's physics. It's unavoidable, which is exactly why that redundant middle pane needs to remain unfatigued, protected from those cycles by the bleed hole's pressure equalization. The outer pane takes all those cycles. It ages. It accumulates microscopic stress. And the middle pane, shielded by that tiny hole, stays as good as the day it was installed. The system is designed for time, designed for the reality that aircraft don't just fly once, they fly constantly for decades. And now think about this from the perspective of a passenger. You've probably sat by a window seat hundreds of times and never thought about any of this. You looked out, maybe watched the clouds, maybe stared at a city shrinking below you, and the window just worked. Silently, invisibly, doing everything it was designed to do. That's the thing about great engineering. You don't notice it. You only notice engineering when it fails. When it works perfectly, when it keeps you safe at 35,000 feet, manages pressure differentials, prevents moisture buildup, and maintains a backup structural layer all at once, it's completely invisible. It just feels like a window. But now you know it isn't just a window. It's a 3-layer pressure management system with a built-in backup, a moisture control mechanism, and a passive load distribution design, all made possible by one hole that looks like a manufacturing defect, but is actually one of the most intentional details on the entire aircraft. There's a reason aviation has the safety record it does. It's not luck. It's not just skill. It's this kind of thinking, applied to every single component, every seal, every bolt, every window on every aircraft. Engineers who ask not just, will this work? But what happens when this fails, and what happens after that fails, and what happens after that? Redundancy, layers, backup systems for backup systems. The bleed hole is a tiny physical example of a massive philosophical commitment. The idea that in aviation, one point of failure is never acceptable. You always build the next line of defense before you need it. And here's the cherry on top, the fact that might genuinely keep you thinking after this video ends. The design of airplane windows, including that bleed hole system, is largely a response to one of the darkest chapters in aviation history. In the early 1950s, the world's first commercial jet airliner, the de Havilland Comet, began experiencing catastrophic, unexplained mid-air disintegrations. Aircraft were falling out of the sky. Investigators eventually traced the cause to metal fatigue around the window corners, which were square at the time. The repeated pressurization cycles caused cracks to propagate from those sharp corners until the fuselage tore apart. The entire aviation industry rewrote its understanding of pressurization, fatigue, and window design after those disasters. The oval and rounded windows you see today, the multi-pane systems, the obsessive focus on pressure cycle engineering, all of it traces back to lessons written in tragedy. That tiny hole in your airplane window isn't just clever engineering. It's the end result of decades of hard-won knowledge, built on understanding what went wrong and making absolutely sure it never goes wrong again. So next time you're in a window seat, look for that little hole. It'll probably be near the bottom of the middle pane. And when you see it, remember, that's not a flaw. That's the whole point.